what I'm going to do now is I'm going to go through some of these examples, not all of them, just a few to get you started so that you can complete the rest on your own. The first example that I'm going to start with is up here in this section where we are identifying the degree of each monomial. Okay, remember the degree of the monomial as defined above is the sum of the exponents of the variables. Okay, so if we look here at part A at x to the 8th, well, the sum of all the exponents there is 8, so my degree is 8. Pretty simple. One variable, whatever that exponent is, that's your degree. Let's skip over to C. Now C has two different variables. Okay, so what we do when that happens is we've got to remember that S really has a 1 as its exponents. And so the degree of the monomial is the sum of those exponents. So 4 plus 1 is 5. So the degree of that monomial is 5. All the way down here at the end to D. Again, same thoughts as we saw in C. All right, we've got to remember again, that's really y to the first power. We add up those exponents, 2, 3, 4, 5, 6, right? 2 plus 1 plus 3 equals 6. That's my degree. Now, when we head back to part B here, I don't have any variables. Okay, so what I've got to look at then is, all right, well, I just have a constant, or I have to realize I just have a constant. And the degree of your monomial when you just have a constant term is 0. Okay, next we're going to talk about how we simplify these exponential expressions, okay, or how do we simplify exponents? What are the rules? How do we know we're done working with it? Well, if you look right here, there are a few characteristics as you read through this that make our expression simplified. Okay, part A is the most difficult to understand, and it says you're simplified when there are no powers of powers. So, for example, powers of powers is something like this, when you're taking a power to another power. You are not simplified if you see something like that. All right, so again, if you see something like this, a power to another power, you're not simplified. You have to simplify that. As soon as you get rid of all of those, okay, then you might be simplified as long as you are able to do the rest of what's listed here. Okay, number 2, each base appears exactly once. Okay, well, what's a base? Well, look at number 1 here. These are your exponents. These are your bases. Okay, so this one isn't simplified because I see my base 3 times. One of the characteristics of an expression being simplified is that each base only appears 1 time. Number 3, all fractions are simplified. Well, that goes along with everything we've known for a very, very long time. And number 4, there are no negative exponents. And I said this from the onset, you can't have any negative exponents in an answer ever. So what I'm going to do here is I'm going to go through number 1, number 2, number 4, and number 9. And then you're going to complete the rest on your own. And we're going to simplify each of these expressions. Number 1. All right, first of all, I have a negative exponent, and I see my base more than once. So there's a couple things wrong with this. I need to simplify it. One of our exponential rules says when we multiply bases together, which we're multiplying, all right, and all of my bases are the same, I just need to add my exponents together. So what I'm going to do is I'm just going to add 5 plus 2 plus negative 3. And when I do that, my result is 4. And there's my answer, c to the 4th. Now I'm going to go over to number 2. And what makes number 2 a little bit different is I have more than one base. I have a base of A, a base of B, and a base of C. Now remember, when you're multiplying the same base together, you add the exponents, okay? So in all reality here, the only exponents I can add together are the negative 3 and the 2 because they share the same base. Now before I do that, realize, right, we have all multiplication here. A to the negative 3rd times a squared b to the fourth times c to the negative first. So going back to being simplified here, there's a couple things wrong. I see a base more than once, and I have some negative exponents. So we're going to have to work through both of those issues here. So let's fix the fact that I see a base more than once. So when I multiply all three of these together, I'm going to add these exponents together. All right, negative 3 plus 2 is negative 1. So it's going to be a to the negative first power times b to the fourth times c to the negative first. Okay, and so that took care of the fact that I had a base that I saw more than once. Now each variable only appears one time. Well, the next thing I need to fix is the fact that I have negative exponents. Okay, I can never, ever, ever answer anything with a negative exponent. So remember, with negative exponents, all right, as you saw at the top when you went through the rules and you did your own examples, okay, negative exponents, I tell my Algebra 1 kids to think flip, think fraction. All right, the negative sign sends that variable to the other side. What we have here really is a to the negative first, b to the fourth, c to the negative first over 1. So when we think flip, anything that has a negative exponent is going to go to the other side of that fraction bar. Okay, remember, this is my fraction bar. So the a to the negative first power is going to go to the denominator. The c to the negative first power is going to go to the denominator. But b to the fourth, it stays. Okay, this is a positive 4. My positive exponent keeps me on the side of the fraction bar that I'm on. So when I fix this, b to the fourth stays. A to the first, c to the first goes down to my denominator. This is my answer. Now number 4. Number 4 starts out as a fraction. I've got some coefficients, and I have some variables, and then I've got these exponents. Okay, so let's go through all the rules. Number 1, your fraction needs to be simplified. All right, and that's referring to coefficients. Okay, we've got to make sure that, for example, 24 over 3, right, is in its simplest form. Well, 24 divided by 3 is 8. That's its simplest form. Now, the W's. We have our quotient rule here. Remember, when we have division of the same base, we subtract exponents. All right, so there's a 1 here. 1 minus 3, because those are the exponents on my W. 1 minus 3 is negative 2. With the Z's, 7 minus 5 is positive 2. Okay, so last rule that's being broken here is I have a negative exponent. So just like number 2, the one we just did, you can think of that as over 1. And anything that's being raised to the negative power, or a negative power, in this case it's negative second power, all right, it's going to go to the denominator. So the W to the negative second is the only thing that leaves and goes down to the denominator. Everything else has a positive exponent. Final answer, 8 z to the second over W to the second. That's my final answer there for number 4. Last one we're going to do on this side of your notes is we are together going to go through number 9. Okay, so number 9. All right, well, what's wrong with it right now? I see bases more than once, and I have a negative exponent. There are a couple different ways to do this problem. All right, I'm going to go through one of the ways. Like, we could fix the fact that I see my bases more than once first. But I'm going to fix the negative exponent first. And this goes back to your power of a quotient property. That's why I'm able to do what I'm about to do. Anytime you've got a negative exponent outside parentheses like this, I can make that exponent positive simply by flipping that fraction. And by flipping, I mean I'm going to write it as its reciprocal. So what was the denominator is now the numerator. X squared, y to the 5th. And what was the numerator is now the denominator. 2x y to the third. And when you do that, this exponent outside becomes positive. So now what I'm dealing with is x squared y to the fifth over 2x y to the third. Next, I am going to fix the fact that I see my bases more than once. So inside the parentheses here, working with this fraction, I really have a 1 over 2, okay? My coefficient here in the numerator is really 1. So I've got a 1/2. Now again, your quotient rule, you subtract your exponents. So 2 minus 1, remember there's a 1 there, x to the first power. 2 minus 1 is 1, so x to the first power. And with the y's, 5 minus 3 is 2. Okay, now in a situation like this, where I have a fraction, what I've got to understand is these variables next to it, if they have a positive exponent, they're coming up here with the 1, or they're going to the numerator. If they've got a negative exponent, well, then they're coming down here with the 2, or the denominator, and again, when that happens, that exponent becomes positive. Okay, but what we have to remember again is this is all inside these parentheses raised to the second power. All right, but let me rewrite this as one big fraction. So xy squared over 2 raised to the second power. Now I have to use my power of a quotient property. And remember, this 2 right here applies to every single thing inside those parentheses. And what I do is I multiply the exponents together. Okay, so this is really x to the first to start, and this is really 2 to the first to start. So for the x, 1 times 2 is 2, so it's x squared. For the y, 2 times 2 is 4, so y to the fourth. And again, in the denominator here, 1 times 2 is 2, okay, or 2 squared. All right, now go ahead and make that 4 there in the denominator. So x squared y to the fourth over 4. And that's your final answer. So as you turn your notes over to the next side, there's some vocabulary terms at the top which you can use that link to define. And then we've got 3 examples here that are going to teach us about what makes something a polynomial and in particular, what makes something not a polynomial. We're going to talk about those rules. So I'm going to go over here and I'm going to start with number 11. Okay, I'll tell you right off the bat, this is not a polynomial. Okay, well, why? Well, why isn't it? I'm going to rewrite number 11 like this. C to the fourth minus 4c to the 1/2 plus 18. Now, in order to do that, okay, I've got to understand this, all right? That the square root of anything, whether it's x, c, 18, 24, whatever, is really that number raised to the 1/2 power. Okay, so this goes back to being able to writing radicals as fractional exponents or rational exponents, and then writing rational exponents as radicals. Okay, this is one thing to kind of put in the back of your mind, all right, to remind yourself that you've got to remember that. So that's why I'm able to write this as c to the 1/2 power. Now, like I said a few minutes ago, or a few seconds ago really, no, this is not a polynomial. Okay, well, here's why. This right here. Polynomials only have integer exponents. Okay, remember integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, numbers like that. They don't include like 1/2 and 3/4 and 5/8. All right, you can only have integer exponents if you're going to say yes, this is a polynomial. Okay, so what I've circled there, that makes that not a polynomial. All right, now as we go over here to number 12. All right, so that rule I just talked about. Are all the exponents integers? Yes. Okay. 2 is an integer. Okay, -1 is an integer. Remember, negative numbers are integers as well. But this breaks the next rule we need to talk about. That right there. You're not allowed to have negative integers as your exponents. Okay? Or kind of broaden the category. You can't have any negative exponents. All right? If you have a negative exponent, it's not a polynomial. So again, this is no, all right? This is no, all right, because I have a negative exponent. Now, you might be saying to yourself, well, I can fix that now. I can make that negative exponent into a positive exponent by doing this. And now you're like, hey, Miss Gray, no, all those exponents are positive. But here's the third rule. You're not allowed to have any variables in the denominator. Okay? All right, so that's, again, if you saw it looking this way, why it would not be a polynomial. So 3 rules that we talked about here. Number 1, you have to have integer exponents. Number 2, you have to have positive integer exponents. And number 3, all the variables have to be in the numerator, okay? Or in other words, no variables in the denominator. So following that conversation, we can go back to number 10. All right, we look at this. Are all the integers positive, or I'm sorry, are all the exponents integers? Yes. Are they all positive? Yes. And are there any or I should say variables in the denominator? No. Yes. This is a polynomial. The last 2 examples I'm going to go through here are number 20 and 21. Okay, up above this you have some addition and subtraction, you have distributive property work, and all of that stuff you should be able to do by this point. 20 and 21 are really distributive property work. There's a little bit of foiling involved, but it's a little bit different in that we're using binomials times trinomials and binomials times each other. And I just want to walk you through the different steps, all right, on how to simplify these. So number 20, I have multiplication. Okay, I'm multiplying 3x minus 1 times 2x squared minus 4x plus 5. So I have a binomial times a trinomial. Now when this happens, you're going to use the distributive property, and you're really going to use it 2 times. Okay, the first time you're going to take this 3x, and you're going to distribute it to all 3 terms of that second polynomial or of that trinomial. And then you're going to take negative 1 and distribute that to all 3 of those terms. Now I'm going to keep it color-coded just so you can see this a little bit easier. And I'm going to start with the green. So 3x times 2x squared. 3 times 2 is 6. X times x squared is x to the 3rd. 3x times negative 4x. 3 times negative 4 is negative 12. X times x is x squared. And then finally, last thing with the green, 3x times 5 is 15x. Now, let's work with the purple. Now, what I could do is I could continue to write this out over here. But what I'm going to do is I'm going to use what's called the vertical method of multiplying polynomials together. And what I'm going to do is I'm going to match up vertically like terms, like this. Negative 1 times 2x squared is the first multiplication I need to do. So negative 1 times 2 is negative 2. And then there's no variables to multiply together, so it's just negative 2x squared. Now, this vertical, or this column, rather, has the x squared. So I'm going to put that negative 2x squared right there. Then I'm going to take negative 1 and multiply it by negative 4x. So negative 1 times negative 4x is positive 4x. And then lastly, I've got negative 1 times 5, all right? But I don't have a constant term up here in green to match it up with. That's okay. I'm going to still write it over here, continuing on with my purple polynomial. So negative 1 times 5 is negative 5. Now, what this does for you is it visually sets up the terms that you need to add together. And you do it column by column. So this first column, 6x cubed, times, or I'm sorry, 6x cubed plus, there's nothing there, so you don't add anything. You keep it. So this is 6x cubed. Now, second column, I add negative 12x squared minus 2x squared. And when I do that, it's negative 14x squared. Remember, when you add like terms together, or subtract, the exponents don't change. That only happens when you multiply and divide. All right, then over here, this column, I need to add 15x plus 4x. and that's going to give me 19x. And then lastly, with my constants, I don't have anything to add to negative 5, so I keep it as negative 5. There's my answer. It's in what we call standard form. We've got 6x cubed minus 14x squared plus 19x minus 5. And by standard form, I mean the first term has the biggest exponent, 3. And then we count our way down. 3, 2, 1, and then our constant, which is negative 5. All right, now I'm going to go over here with 21. And 21 is obviously different. I'm multiplying 3 binomials together. Now, I'm going to use the vertical method again, but this is going to take me a couple steps to do it. All right, and I'm not going to get to that vertical method until after I've multiplied these first two together. Okay, now, when you start this problem, you really have some choices. You could multiply those first two together. All right, you could start by multiplying the last two together. Or, you might get bored and want to multiply the first and the last together. And by multiplying these together, we're foiling because we're multiplying 2 binomials together. But whenever you're in a situation where you have more than 2 binomials, in this case we have 3, you need to just choose 2 of the 3 to FOIL together first and then continue on from there. So what I'm going to do is I'm going to pick the first 2, these 2, and I'm going to FOIL them. First, outside, inside, last. Okay, so first times first, 2x times x is 2x squared. Outside times outside, so now it's 2x times negative 1, which is negative 2x. All right, inside times inside, 3 times x is 3x. And then last times last, which is 3 times negative 1, which is negative 3. So I'm going to combine my like terms here. That's the last step of FOIL. So I have 2x squared plus x minus 3. All right, I combined the negative 2x plus the 3. All right, and that gave me a positive x. Now, what I haven't touched yet is I haven't touched this x plus 4. Okay, so I'm going to bring it back. And now, I have the exact same problem that we had in number 20. All right, the only difference with number 20 was the binomial was in front. Okay, with this problem, our binomial's at the end. No, it doesn't matter. If you're more comfortable moving this to the front and doing the multiplication the same way we did with number 20, by all means, do it. Okay, there's going to be no difference in your answer if you do everything, if you do all the math correctly. All right, I'm going to go ahead and I'm going to keep it over here and just show you that we can do things the same way even though they're in a different order. All right, so again, I've got 2 sets of distributive property. I've got the blue, x times all those, and then we'll work with green again. And let me do this the right way. The green's with the 4. We can use all that. So with the blue, x times 2x squared is 2x to the 3rd. X times x is x squared. Negative 3 times x is negative 3. And then with the 4, 4 times 2x squared is 8x squared, so that goes in this column. And then I've got 4 times x, so that's 4x. And then negative 3 times 4, which is negative 12. All right, go ahead and add these together. All right, let me find my highlighter. Here it is. Okay, so 2x cubed, nothing to add to it, so it's just 2x cubed. When we add the squareds together, 8x squared plus x squared is 9x squared. Negative 3, negative 3x plus 4x is x. And then finally, negative 12 plus 0 is negative 12. And there you have your answer, written in standard form. Okay, the last thing I want to go back to, and this is my apologies for doing this out of order, is up here with number 10, 11, and 12, so go back up to the top of your paper. It does ask us not only to determine if each expression is a polynomial, but if it is, state the degree of the polynomial. So 11 and 12 are not polynomials, so there's no degree to them. So the only one we got to worry about in that respect is number 10. So in number 10, well, what's the degree of this polynomial? First, look at each monomial and find the degree of that monomial. So this first monomial, the degree is 5. This second monomial, your degree is 9. Right? And all I did was, with the purple there, I just added the exponents together. Now, the degree of your polynomial is not 14. Right? It's not, you don't add the 5 and the 9 together. Rather, you look at the biggest degree of each individual monomial, like 9's bigger than 5. So 9 is the degree of your polynomial.